Buenos días, bienvenidos a todos. Hoy vamos a dar la segunda sesión de estas charlas de divulgación científica, más que nada, y de codificaciones, a cargo de Goldman, quien es, fue el presidente de la Sociedad de Televisión, de Ingenieros en Televisión, la SEMTI, hasta fines del año pasado. Realmente es un honor contar con su presencia, es una figura de mundial importancia y para nosotros es muy importante poder compartirlo con ustedes. El señor fue durante 2 años presidente de la SEMTI, han resuelto un montón de cuestiones y sobre todo su mayor logro fue el haber lanzado la norma 2110, la cual es muy importante para todos los accesos y comunicaciones entre equipamientos y sobre todo en el área de IP. También nos acompaña Ronaldo, que es de la empresa MediaKind, y vamos a hacer una demo después, vamos a dar una breve explicación primero de todo lo que es Ultra HD y las implicaciones con el HDR, las codificaciones, etc. Vamos a ver una demo allí sobre Ultra HD, y después en la segunda parte, después de un break, vamos a hacer una sobre normativas, los últimos códex y el futuro que tienen aquí en el roadmap inmediato, y cuáles serían sus aplicaciones, lo cual también es muy interesante. Después vamos a hablar de virtualizaciones y microservicios, que también tenemos una demo sobre cómo se puede presentar una cuestión de microservicios con virtualización, ¿no? Así que desde ya muchas gracias y esperamos que puedan sacarle el jugo a esto. Posteriormente les vamos a mandar toda la presentación a todos ustedes para que la puedan tener. Es muy importante realmente que puedan participar de esto porque es más que nada divulgación científica, ¿no? Muchas gracias.
Gracias, buen día a todos. Matthew va a estar hablando, como ya lo dice, por casi 2 horas aquí, un poco más, pero solo quería decir algo, un minuto, sobre qué es MediaKind, para quien tenga el contexto, y hacer la asociación. Entonces, MediaKind, para quien no sabe, era Ericsson Media, o sea, Ericsson vendió 51% y quedó con 49%. Y es un spin-off de toda operación de media de Ericsson, donde desde 2017 Ericsson compró varias compañías, imagino que recuerdo, o sea, la parte de Thunberg, Envivio, Media Room, Microsoft, Azuki, la parte de Fabrics, que hoy básicamente toda la parte de cloud media que tenemos, toda la parte de compression y la parte de TV platform. Entonces, aquí obviamente no vamos a hablar nada de producto, básicamente la tecnología, como comentó, pero cosas como microservicios que vamos a hablar después es la base de todo el producto de nosotros. Entonces, todo de cloud ready, etc. Y muchas gracias. La idea, por ejemplo, de hacer ese tipo de trabajo con BVS es parte de la, digamos, nueva marca, nuevo tiempo. O sea, tener más presencia en Argentina, está con partner muy fuerte y está más cerca de los clientes. Entonces, básicamente es un mensaje que quería compartir con todos. ¿Okay? Muchas gracias. Gracias. Perfecto. Your time to make the show.
It's my time for the show. Good morning, everyone. So, I am going to do you a favor and not try to do this in Spanish, okay? Because nowhere near good enough for doing that. But anyway, thank you all for coming today. We have 2 sessions. Each is 90 minutes long. The first one is hot topics in TV technology. Then we'll take a 15-minute break. And then hopefully your brain will decompress because it's a lot of information. And then we'll start the next session, which talks about migrating, our industry migrating to all IP and what that means and why, and also software virtualization topics. Okay? So without further ado, in the hot topics for TV technology, I have 3 parts. Each will be about 30 minutes long. You can stop me to ask questions. If you have anything, just raise your hand, or if I'm not paying attention to you because my brain is elsewhere, just shout out loud. And or you can wait to the end of the section, and you can write down your question, and at the end of the section, I'll ask for that. We're going to talk about ultra high definition television, emphasizing the new high dynamic range features, because I think from the feedback I've received, that's what you're most interested in. And then It's time for a new codec, so to speak, but there's so many to pick from. I don't know how many of you are involved in the compression aspect of your business, but I'll talk about high efficiency video coding and the new open source AV1. And then lastly, we'll talk about the updates on adaptive bitrate streaming. It'll be of interest to you, particularly the low latency coding for the common media application format that's brand new for doing streaming. So we'll start with the first topic here, and that will be ultra high definition television. So to understand ultra high definition television, you need to understand the human visual system. And I could spend an hour just on this one topic, but we don't have that. So I'll try to sum it up pretty well. Your eye sees very differently than a camera. The way a camera sees is all the light enters into the sensor in the back of the camera and it looks at it at once. In the case of the human visual system, that's not how it works. You have varying degrees of resolution in your eyes around the outside. It's only in the very center of your eye, which is known as the fovea centralis, where you have very detailed, sharp imaging. So what happens is you don't know you do this, but you don't actually look like a camera at everything, all the light that's coming in. You actually have something called stochastic motion, which will scan across an image, and you recognize things by the images. That's why sometimes you think, oh, I wonder if I know that person, because your brain is calling up an image that it has stored for something else, and that's why sometimes you think it's deja vu, so to speak. In the center of your eye, you can resolve about, on average, 1 arc minute of resolution, which means anything that's more detailed than that you won't see. And if you're too far away from it, you won't see it, because it's about what you can resolve. Really good vision, maybe half of that, 0.5 arc minutes, but that's when you're looking at a screen. So what does this translate to? So it means there's a proper viewing distance for looking at TV resolution. Now your eye is three-dimensional, so it's trigonometry to do that. But you can simplify the equations based on screen size because our screens are what? They're 16 by 9. So once you know that the image you're looking at is a rectangle, you can actually use right triangles and simplify it. So using that 1 arc minute of resolution, the proper viewing distance is based on the resolution of the display. So if it's HD, or 1920 by 1080 pixels, in order to be able to resolve that with your eye, you need to be sitting within 3 picture heights back from the display. It will look like the top picture here. So it fills up about 1/3 of your field of view. Your central field of vision is about 100 degrees. We'll just call it 90, so about 1/3 of it. Well, that's the proper viewing distance for an HD TV. So if you look at this, 3 picture heights back. Here's one. If you lay the set this way, that's probably to about right here, right? So 2 would be about right here, then 3 would be about the middle of the room. All of you sitting in the middle of the room this way, you're seeing high definition television. All of you further back, you're seeing something less than high definition. The TV's broadcasting, or not broadcasting, but displaying HD, 1920 by 1080. But because you're too far away, your eye can't resolve it. Does that make sense? 3 picture heights back. The reason this is important is because if you're looking at a 4K TV, which is known as 2160p, that's 3840 by 2160 pixels, 2 times in both directions. Same size TV, but now it has 4 times the resolution, or 2 in each direction. Remember, your eye can only resolve so much. So what does that translate to? You need to be 1.5 picture heights back from the screen in order to resolve 4K. So we do the same thing. 1.5 comes out to be about right here, which means the front row, maybe if you have good eyes in the second row, if this were a 4K TV, which it's not, it's HD, but if it were 4K, you can resolve the 4K. Everybody else in the room, to the middle of the room, you're seeing what? HD. People in the back, you're still seeing the same resolution you saw before. The reason I stress this point so much is because if you're offering content either as a service provider or a content provider. And your marketing department is advertising, look at this great new football match. We're showing it in beautiful 4K. And then you run down to the store and you buy yourself, well, I don't know, how many people have a TV this size? This is 60 inches. Anybody have this TV this big at home? Oh, you clearly have the wrong priorities. Okay, this is a pretty big TV for most homes. Okay, in the US, 50 to 60 inches is starting to become common, but in many countries, it's still 40 to 50. Okay, but for the purposes of here, just think about this. It doesn't really matter what size screen we're talking about. If you're sitting 3 picture heights back from it, and most people do, you probably are sitting about 2.5 meters back from your display. So somewhere 2.5 is the right viewing distance for HD. But if you run out to the store, you spend all the no money to buy a new 4K TV because you want to watch football on it, you sit yourself in your living room and you're still sitting at 2.5 meters back, what are you watching? HD. It's important for you to understand that because people are going to say, what's so great about the new thing? We obviously want the new technology, but it's really great. The other thing is because you're sitting twice as close for the TV for the size, it fills up now 2/3 of your field of view, right? Because you're sitting that much closer to it, which means you're more immersed in the picture, which means you're going to see more motion artifacts and any other type of imperfections in that. If I had more time to spend, I'd talk about the impact of frame rate and things like that, but that's not for today. But these charts, you'll get a copy of the presentation if you ask for it from BVS, okay? I don't have it quite ready yet, but I'll have it by the end of the day today. So these are from the internet, and they just help you understand that. This is a much better chart on the right, but it's pretty complicated to read. So once you get used to looking at this one, then you can figure out that one. But basically, what we were talking about before, if the average screen size, right, is, let's just say 45 inches in Argentina, if you're sitting at 1.8 meters, you're just at the edge of the average person resolving 4K. So if you're more than 1.80 meters back, you're not going to see 4K. You want to be in here. Now, some people have much better than normal vision. You start to get old like me, I have a different problem, presbyopia. I have perfect vision, but I can't see things that are close to me. My arms aren't long enough anymore, right? So it's the same thing here. The reason I point that out is the same viewing distance applies towards what? Who has a tablet here? Anybody have a tablet? No, we'll just use this. So do you agree this is about the size of a full-size tablet? Right, so if you run an airplane and you're sitting at the seat and you put this in front of you, you're about at what? 2 picture heights back. And you can adjust that, which means what? If your tablet does 4K, which I think the new Retina screens with the iPads, I think are 4K, right? I think they are. You can correct me if I'm wrong. Anyway, if you do that, you can resolve 4K. So you can actually look at 4K. Of course, I can't see much in here because of my presbyopia, but that's a different problem. Right? So I just want to make sure you knew this. This is very, very important because this is the impact of 4K. It really does look better, but you have to be sitting at the right distance from it. And if you go into the electronics store, I don't know what you have here for stores that sell like home theater systems. I'm not sure how common that is here, but they'll have you sit in a nice couch. They'll spend all this time explaining how to place the speakers around you, so you have proper 5.1 surround sound, or if you get the new, they have these new sound bars now that just sit in the front, but they fake out your hearing, right? And it sounds like the sound's coming from around. Very good, but they'll tell you all about all the audio stuff and what you need to do for that. But no one tells you that you have to sit at a certain viewing distance. I'm not even sure they know. You know over time, because if you're using this content, you're going to say, I don't see any difference in that, and that's why. I spent so much time on this because I want to talk about this, okay? Now we're talking about your perception of what is resolution. So I have one on the left does not have the dynamic range. In other words, dynamic range, big fancy word, dynamic range. But dynamic range, like anything else, even in audio, you can have dynamic range. Anything can have dynamic range. You know, when you broadcast radio over the air, right? They take the lower and the high frequencies and they do what? They compress them. Not video compression, but it's just range compression. So the low bass sounds are brought up high, so you don't get that deep booming bass over the radio. Close, but in the very high, I'm talking about regular radio, not digital radio. But the high frequencies are gone too, so you get most of the noise in there with FM broadcasts anyways, right? Unless it's digital. This is the same thing. So the dark areas have been lifted higher. They're not black anymore. They're in the gray area. And the really light areas have been brought down as well. So basically, the end result is this looks more blurry. Now, since you're sitting far away from it, your eye translates it to having less resolution. Your eye sees the blacks here against the lighter areas as a sharper transition. The contrast, it's contrast on your TV. The contrast, the difference between the dark areas and the bright areas, that is dynamic range. So, important point, your eye interprets dynamic range as spatial resolution. So this picture on the right, because it has higher dynamic range, looks more real to you. Just looks more real. So, the other thing about high dynamic range, it's not about a brighter display. Yes, it is a brighter display, but it's a brighter display that you use in very small portions to emphasize the dynamic range difference, the contrast difference. So, if you have a sun, looking at the sun, or a bright light source, you're at, maybe it's a night scene and you're on some type of a sports court or a pitch, and they have lighting. You can see the areas. You emphasize that you want that to actually look much brighter than the areas around it. And similarly, if it's dark in here, or in the well where the tire is over here, the cop tire, you want to be able to see the tread that's on that tire. But the difference is between in the shadows of the light levels there, very little. Your eye is not as sensitive to dark levels. So a lot of times the black level is too high and you can't see anything in it. I doubt any of you can see the tread in there. It's there. If this were a high dynamic, I'm emulating here, right? This is a regular display. It's just now what we call regular displays are what? Standard dynamic range, SDR. But it's just the old stuff versus in high dynamic range. If this was in high dynamic range, the reflection of the sunlight off the car, hey, you've gone through parking lots here outside. You can see it a little bit on the coffee containers out there and the water pitcher out there. To see how bright that little spot is where the sun is reflecting off the water pitcher out there? That pinpoint specular highlight is much more bright than the rest of it. That's what you want to do with a high dynamic range TV, that one little spot. The rest of the picture you want to be the same as it is now, the average light level. But having that one spot be brighter, even though it's nowhere near as bright as that, because I'm squinting a little bit, that's so bright. Now, unless you plan on watching TV with sunglasses on and a hat when you're inside, right? You don't want it that bright, but you would like to have the dynamic range light. But that light would be very, very bright where the white is, just in that one little spot. But at the same time, you'll be able to resolve the tire tread inside that well, just like you can in real life. That's why high dynamic range is so exciting. It's making pictures look much more real than they are today. I can't show you it on here, but I hope you get the concept here. In a regular television today, or a standard dynamic range display, the difference between the dark areas and the bright areas are only about 25%. There's not enough dynamic range. Dynamic range is measured in terms of luminous intensity. The measurement of that is candelas per square meter. Now, as an engineer, you get tired of saying candelas per square meter. So they have a shorthand name. It's not an SI name, but it's a shorthand name. It's nits, N-I-T-S. So the production standard for television, the maximum white level is 100 nits. 100 nits is equivalent to about a 100-watt light bulb. Not looking at it, just the light it throws in the room. If you look at a 100-watt light bulb, it's much brighter, but the light it throws in the room. On a high dynamic range display, it could be 100 times more. Okay, so it gives you that much more field. But remember, it's only that high in a very small area, the specular highlight. If the whole display was brighter, what would you be doing? After 5 minutes, you'd be doing this. It would fatigue your eye. You don't want that, right? You want to watch television. So it's very important concept. It's not about brighter displays. Now, we talk about high dynamic range. We're really talking about 3 different technologies. We talk about the high dynamic range itself, right? Which means you can see the details in the dark areas simultaneously with the details in the white, which would be the picture on the right. This is how you take a camera shot. You usually get one or the other, but you can, unless you're in high dynamic range mode. It also has a wider color gamut, the different colors you can see. So, from here, this chart here is called an XY chromaticities chart. It shows you the human vision colors. So that's this bullet shape here. I hope it looks familiar to you. We know we see in 3 basic colors, right? RGB, red, green, blue. Red's here, green, blue. If you have 3 different colors in a 2-dimensional space, it forms a triangle, right? So RGB forms this. Would it surprise you to know that those great, fantastic, high-definition televisions that you have, those are the colors that can display in the orange. None of those colors out here it can display. Now, you say, well, it looks fine to me. It does, because you're looking at the TV. They're muted. The color, the tone is changed. It still will look green, red, or blue, but it just won't have that brilliance to it, right? So if you could simultaneously look at something on a TV and look at something outside, which you normally can't, because if you're outside with the TV, the ambient light flushes the whole TV out. You can't see anything. What happens? There's no dynamic range, right? It's just all washed out. But if you could see it, it would look better. And this is called 709 for those that know the ITUR standards. Okay, so this is 2020. That's what a 4K or a UHD color space is. Still not perfect, but a lot more greens, some blue, and definitely more red. The brake lights on the back of your car, your automobile, the brake lights, they're not in this space. They're out here. Grass, most colors, grass will do that. It's up here. So what does that mean? That means if you have the 4K or the Ultra HD color space, the colors look more real to you too. They look more brilliant. Now I want to be careful about this. This is not about making it look cartoony. You don't want to change the color so that it looks like you're looking at a cartoon or make it overly bright. It's in the proper color, that's all. It looks more muted on a regular TV. It's hard to explain that unless you can see the difference between what something is on the other, now that's called wide color gamut. The old one is called narrow color gamut, okay? The last one is sampling, bit depth. So most everything we look at today is in digital, from digital files, right? So you know it's not a waveform anymore until it gets translated to the display, then it becomes a waveform, right? So with that in mind, digital values, right, are approximations of what the real waveform is, right? But the size of the field that you have in there limits the number of different values you can have, right? For almost all of consumer applications today, for entertainment, it's 8-bit. You guys know that, right? In the studio, it's 10, but it's 8-bit for consumers. 2 to the 8 is what? 256, right? 256? That's the maximum number of levels you can have. Because some are reserved values, it actually is about 225 different levels, but for the purposes of here, we'll just call it 250. So think of that. You got this beautiful sunset happening here. And you have all those colors and brightness. Where the sun is, it's really bright still. As you go away from the sun, it gets darker and darker. The tone is much more yellow. As you move away from the sun, the tone starts to shift towards orange. But it happens very slowly, right? Like as if you're walking up or walking down a ramp. It's continuous values. But I only have 8 bits. So what is that the same as? That's the same as walking up. It's not a ramp anymore, it's what? A stairs. So it's the same color until you get to the end of the stair that you're on. And then what? You jump up, you take a step up to the next stairs. So what happens at each one of those points, right? I think you can see it on the left-hand side. Do you see the banding?
Yes.
Most people think, oh, that's bad video compression. It has nothing to do with video compression, although video compression makes it worse. That banding is caused because you only have 250 levels, both in brightness, right, as well as in color. So that limits the effective dynamic range. So you need deeper sampling for Ultra AT to get rid of that. It happens to be that 10 bits is now brought into this when you're looking at the high dynamic range stuff. 10 bits is still stairs, it's 4 times more steps, but it works really well because unless it's computer generated color or brightness, the natural noise in the environment, what you see, do you know what dithering is? That's when your eye can't resolve a certain level, so it kind of looks like it's like noise around the background. You don't see it because you're used to it. But that natural dithering that you have with natural images sort of fuzzes out where the steps are. And they're still there, but you can't see them as well. That's why 10 bits looks like it's on the right. Now, obviously, just like with dynamic range, just like with color, this is an 8-bit display. I've emulated that, right, to make it look smoother for you. But it's very important to realize that when you say HDR, it's all 3 of these combinations together. So most people are talking about HDR. They mean all 3 of these. The other important point is HDR is equally applicable to HD or 4K. So there's 4K on the left, HD on the right. Works the same. Doesn't matter what your spatial resolution is. It all works the same. The other important point is your eye is much more sensitive to contrast, as that image before showed us, right? That contrast you recognized all the way in the back of the room. It's not distance dependent. Obviously, if you're so far away from the display that you can't see what you're looking at, then it's clear. But what I'm saying is you could actually see someone holding up a lighter or a candle several football fields away. You'll see that light. Your eye is very susceptible to brightness, which is why dynamic range is such a great thing. I hope that's a good explanation of it. So in order to understand how this works with televisions, you need to know the concept of a color volume. So here's that XY chromaticity chart, 2 dimensions, right? So you can see colors. If this was only 1 dimension, what would you have? Black and white. You'd have gray. You wouldn't have, this would collapse this way, and you just would see gray. So represent the color 2 dimension. We're going to take that, and we're going to lay that image down flat on the left. So that's X and Y. Z, make it a 3-dimensional image. Vertically, that's going to be what? That's your dynamic range. So it's a combination of your 2-dimensional colors and your dynamic range that creates a color volume. Okay? That's what you see. Inside that smaller triangle there, that's standard dynamic range TV with narrow color gamut. See it in there? The bigger image on the outside, that's high dynamic range with the wide color gamut. You can see it's much more, right? Because it's high dynamic range. Let's see how observant you all are. Anything else that's unusual about that color volume picture? Come on, I know I got really sharp engineers in the room here. Is it?
That edge.
The edge is kind of weird. That's because, that's not what I'm looking for, but that is true. The edge is blue. Your eye, because coincidentally, is not as sensitive to blue as it is to other colors. That's why that dips like that. You could spend the whole college course talking about color imagery. We don't have that. We have 5 minutes. How about the scales? Look at the scales I use there. Right. The Z dimension is what? It's a power scale. It's logarithmic. X and Y are linear. If I made Z linear, how high would that be? Yeah, 5, 10 stories high? Do you understand how more of an impact high dynamic range has on you now based on this? How many here have actually gone into to see a demo of high dynamic range on a real TV? Right, this doesn't really capture it. You know when you're looking at it, it looks fantastic if the demo's done right. Now, let me explain what I mean by that. But I'm a little bit older than most of you in the room here, so maybe you haven't done this, but 20 years ago, when we first brought HD out, high definition television, people were showing demos of HD versus SD, and they were horrible demos. So people were saying, I don't really see the difference because the material wasn't, the content didn't look that good, right? Same thing. If you show a high dynamic range demo and the content's not that good, you're not going to see it. But on good content, it is outstanding. You go, wow, what a difference it makes. In my opinion, this is me now, not MediaKind, not dynamic range to television is the most significant impact to television since color was added to black and white. Notice how I didn't say the same about 4K. It's still cool having that extra resolution, but because it's distance dependent, and most people aren't going to sit at the right viewing distance for 4K. Some will, I will, unless my wife yells at me for having the couch so close to the TV. But anyway, color vines. Why am I talking about color vines? Because every display that's a HDR display, the technologies are different, the manufacturing is different, they all have a different response. Some displays can go to 0.001 nits, some can only go to 0.05. That's the dark area. How black is the black? Remember, black levels are important because that gives you that lower black, which gives you that more of a contrast edge, which looks what? Sharper to your eye. And also seeing the subtle details in the dark areas because your eye is not as sensitive when it's dark versus light. So the difference between something that is 1 nit and 2 nits is not much. I mean, it's a huge difference to your eye being able to recognize that. But if something is, say, 2,000 nits versus 3,000 nits, they're both really bright, but you're not going to be able to tell if it's 2,000 to 3,000 or 2,000 to 2,900, right? It's going to look just as bright to you at 2,900 as it does at 3,000. But I can tell you 1 to 2 nits, if you go 2 to 3 nits, you can absolutely makes a huge difference on the eye because your eye can't see as well down there. So any changes in that makes a huge difference. So because you're mapping what is stored in the content to what the display is, you have to do color volume mapping. And there's both tone mapping, which is the brightness, the intensity or luminosity, and gamut mapping, which is the color. Most people just call it tone mapping for both. But it is a 3D color mapping option. Now, I really should add another slide to this. So maybe when I update this presentation, I'll put another slide. But the art of television is doing what? I'm not talking about the device itself. I'm talking about the concept of why we have television. It's so you could be somewhere else and see something that's happening, particularly for live events, right? It's so you don't have to be there. You're imaging. You're taking scene light. You're converting that to something else. What is that? A bit stream, right? Used to be analog waveforms. Now it's a bit stream. That's a console. It's going light to this electronic bit stream. And then when it comes into your living room, you're converting it back to light again or on your tablet so you can see it, right? That's why it's called television. Across see vision, right? And so you can see something remotely. To do that, you have to have something called a transfer function. You have to convert from one domain to another. So what is the device? What's the transducer, right? What's the device that converts scene light to an electronic bit stream? A camera, exactly. So it's going from scene light, bear with me here. It's going from scene light to an electronic bit stream. That's the transfer function. So light is optics. The bit stream is electronic, so it's called an opto-electronic transfer function. That's what a camera does. And every camera has its own transfer function. And it's called an OETF. You're going to see this everywhere in HDR discussions. They're going to talk about an OETF. With standard dynamic range, does anybody know what the OETF is called? It's actually in BT 709, the same as the color imaging web. It's called gamma. Ever heard of gamma? Okay, gamma, the equation is L equals V to the power of gamma. L is your luminosity, the light you see. So the light you see is equal to the voltage level, which, as you know, analog to digital, voltage level is equivalent to a value in a bit stream, right? To the power of gamma. That's what gives you these curves. That's why I need to add another slide in front of this because it shows the curve. everything is not reproduced exactly. You're not going to reproduce at the other end. What's the transducer that produces it back to a image? Electronic bit stream to a light. So that is an electro-optical transfer function, an EOTF. Fancy names, but you guys already know this stuff. It's just scientists talking, right? So you're converting that. Now, if it were a perfect system, what that display would be showing you is exactly the same as the scene light. So let's look outside this bright sunny day again. Even with high dynamic range, do you think we're going to reproduce that specular highlight that's on that glass water container that's nearly burning out my retina right now by looking at it? Of course not, because again, you're not going to wear sunglasses inside to watch TV. So scene light and display light are different, but I hope you can see you're converting those values to something you can represent. And if you have a better EOTF, electro-optical transfer function display, you get a higher dynamic range. So gamma is very limited. It's only like, I think, 0.5 nits to 100 nits. The production standard is 100 nits. The production standard for HDR is 0.005 nits to 10,000 nits. Now, the displays can't do that. If you have, I don't know if you've looked at HDR displays. Most of them today, if they're LCD technology or an LED lit, sometimes they call them LEDs, but LCD technology, it's an LED lit backlight on an LCD display. If it's a standard television out there that's not high dynamic range, it's probably 300 to 400 nits, even though the production standard is only 100. But an HDR display, if they're LCDs, are about 1,000 nits. The good ones are about 2,000 nits. The pro monitors we have in our lab are between 4,000 and 6,000. It just makes the highlights much brighter in the dark while keeping the dark areas low. So you get what? You get that dynamic range in there, right? So because of that, we have to convert this back and forth. So on the horizontal axis here is a reference display. That's in terms of luminosity, so nits or candelas per square meter. You can see we got 0.001 to 10,000, even less. If the target display, what I'm showing that light on, can reproduce exactly what it was, the production display, of a colorist, right? The production display, the line will be linear. See the dashed line? But there's two things that happen. Because TVs aren't perfect, and I don't know about you, but you pay a lot less money for a consumer product than you do for your reference monitor in your facility, right? So you have two things that happen. The black levels get lifted. This is 1, 2, 3, 4, 5 different TVs I'm showing you. The black theoretical TVs. These aren't real ones. These are theoretical. So this is called an ankle because the ankle, like think of your ankle and your foot, the low levels can't reproduce the same. They're higher. And you have a knee in the curve at the upper end where you're not producing the high as much. So that's a mapping. Remember the color volumes? That is a mapping of the electronic bit stream from the reference display to the electronic bit stream fed to a consumer display. So what do you think that transfer function is called? EETF. Or equivalently, if it's the output you're looking at, it's an OOTF. It's electronic transfer function or opto-optical. And you need to do that. That's why we have that color volume mapping. Because each TV has to map from whatever the respective amount is. Now, how do we know what to map? We have to know what's in the bit stream. And we have to know what the exact curve is, that transfer function. Everybody knows gamma. That's your SDR one. But unfortunately, in our industry, we could not agree on one transfer function for HDR. So just like what's so common that happens in school now, where it doesn't matter who won the football game anymore, everybody gets a trophy, right? Same thing with HDR. Everybody got a trophy. So there are actually 6 to 7 different HDR systems out there right now. It is the antithesis of standardization. It's the exact opposite of what you want to do. I'll get off my soapbox now. So I'm going to explain some of the basic systems. There's 2 different types of HDR systems. Again, that's the transfer function, the HDR. The HDR system either defines an EOTF like gamma or an OETF. Okay? either direction. You're either describing the transfer function from the terms of the image capture, which are being scene deferred, or you're going to describe the transfer function from how you're putting it on the display, which will be display referred, right? So you're going to have scene deferred, right? All right, so if you don't change the value over the entire scene, in other words, the transfer function is the same, it's known as static. Static can actually be over a 2-hour theatrical or a 30-minute episodic television show. You could have it all be static. If you think about it, the ultimate static transfer function is SDR. It doesn't change, it's always gamma, right? You might tweak it in your studio if you're trying to emphasize something, but it's mostly the same, right? So the two main methods are known as perceptual quantization, that's what PQ is, and hybrid log gamma, that's what HLG is. You don't need to know the details. If you know what I'm talking about, it's great, but if you don't worry about it. PQ, perceptual quantization, the transfer function curve matches the human visual system near exact. Perceptual quantity. It's defined in SMPTE Standard 2084. Does everybody here know who SMPTE is? Society of Motion Pictures and Television Engineers. Full disclosure, I was president the last 2 years. I'm not anymore. I'm still on the board, but I'm not president anymore. I'm past president now. So SMPTE is an international standards organization that defines professional media standards. I know you guys all know what SDI is, right? You use it everywhere. SDI is about 3 dozen standards, depending on the speed and what it's carrying. Those are all SMPTE standards, okay? Just using that as an example. You're gonna wanna know that later for my session later today. But SMPTE also defined the perceptual quantization function, the HDR transfer function. It's also defined in an ITU document known as BT 2100. But remember how HDR is defined in terms of 3 things. The actual transfer function itself, the HDR, the wide color gamut, which are colors, and the bit depth. 3 values. So PQ10 is the combination of the perceptual quantizer transfer function known in SMPTE Standard 2084, the wide color gamut, which happens to be defined in BT 2020, and 10-bit sample depth. And we needed 10 bits because you need that extra space. Right, all 3 of those together. PQ, because it matches the human visual system, is displayed referred. When you produce a P2 content, you actually have a colorist sitting at a reference monitor that hopefully can do 0.005 to 10,000 nits. Many of them can't go that high, but they're at least 6,000 nits. And the colorist makes it perfect. Now, why would you want to do that if most consumer displays are 1,000 nits today?
Archival.
What was that?
Archival.
Exactly.
Future value.
Because what are TVs next year going to be? They're already 2,000 nits, and I wouldn't be surprised if someone starts coming out with a 3,000 nit one. So if you're producing content like motion pictures or theatricals, you want them to be in the best archive format possible. Same thing with people producing things in 4K. Not a lot of people have 4K now, but they're being produced in 4K for archival purposes, same type of thing. So for pre-produced content, because it matches the human visual system the best, most people are using PQ. And the simplest form is to have it static, not change, which is PQ10. I'm going to leave this for a second, talk about the other one. The other one is easier to use for live production. And the reason why is because you don't need someone sitting behind a reference monitor. The event is live. What you need is for the live thing to look good as it's happening. So you want to have the on-site broadcast engineer be able to tweak one type of a knob. It's usually, a brightness control type of knob, right? And of course, what are you used to looking at? Gamma. But gamma doesn't go high enough. It only goes to 100 nits. And if you use the same curve as gamma to go to 10,000 nits, you run out of bits. So you can't actually carry it within 10 or 12. You would need a lot more bits, which is too expensive to do. So they do a hybrid curve, hybrid log gamma. So it's a hybrid curve that uses gamma at the lower level, and there's a log curve higher. And it's mostly used for live production today. So HLG10 is another static system, uses the same wide color gamut, BT, the BT 2100 or BT 2020, the same same 10-bit sampling depth, but it's now being captured at the scene, not with a colorist. So it's this scene referred, and it's relative light levels. The guy's adjusting enough. These are absolute numbers. These are relative numbers. I know this is, I really could spend a week telling you about these transfer functions. I'm trying to take concepts and make it simple and different here. So you have these two, and you're always going to have these two because of different preference. Will HLG be the preference for live 10 years from now? I don't know. Right now, it certainly is because it's easier to produce in this, particularly when it's static. The other thing is because this is relative, it's just a relative number, you don't need any metadata. Does everybody know what metadata is? Metadata is data that describes something. How many people here play with picture aspect ratio or active format description? When they're doing development, you do, so you know what I'm talking about. Okay, so for those that do, I'll explain this. If you don't know what it is. Real simple. Some pictures are 4:3, the old SD, right? HD is 16:9 moving forward. So what if you had something that was produced for HD, but you want to show on an SD? You can do one of two things. You can letterbox it, which means you're cutting the wings off, or you could, excuse me, I said it wrong. You could, you could center cut it, which is cutting the wing. I don't know what it is, not enough sleep. Let's start again. You can cut the wings off, which is known as center cutting it, because you're cutting the center out. And then you can show that center on your more narrow TV, the old SD TV. Or what if there's interesting information in those wings? You have to do what? You letterbox it. It looks like a letter inside the black bands in the top and the bottom, right? How do you know which one to use, which one's the right one to use? Because most people like the look of center cutting better because it fills your whole screen up. People don't like seeing black bars at the top and bottom, right? Okay, then why don't we just center cut everything? Because what if the thing you're talking about, like you're in a theatrical, or an episodic, and one person's talking to another one across the table and you center cut it, both people are cut out of the picture, right? But normally happens is you pan and scan, you cut one person out while they're talking and cut the other one out, right? How do you know what to do? Active format description. It's metadata that doesn't tell you what to do, it tells you what you have. And one of the things it can tell you is I have a shoot and protect center cut image here, which means if it's shoot and protect center cut, you can drop those wings and there's no required information there. Otherwise you need a letterbox. The same thing happens with HDR. The metadata tells you what your low light levels are, what your mid-tones, your faces, and your interior colors are, and what your specular highlight maximum level is, so that when you're trying to reproduce it, you know how to map that color volume. Without having information, you don't know what color volume you have. That's the disadvantage of PQ, because it requires that you know it is, because the guy's doing a reference monitor, you don't know what he's using. You can assume it's 0.001 to 10,000 nits, but what if it's not? Here, you don't need metadata because it's like a volume control for light. You just turn it up and down, and it's based around, usually around 1,000 nits is the level. So does it display as good or accurate HDR? No, it does not, but the trade-off is its simplicity. So how do I pass the metadata? Because PQ10 has no metadata. There's something called HDR10. Same thing as PQ10, but it adds in reference display metadata. Now it's static, it doesn't change, but at least you get it. So when you go to play like a Blu-ray disc, or you download something, you're streaming it off of, say, a Netflix or something like that, if it's HDR, it will have the metadata. But it's specified by the Blu-ray Disc Association, and a lot of movies that are stored have it, okay? It's 2086. Now, if you carry it in a compressed stream, it's carried in something known as a supplemental enhancement information data. How many people here deal with compression? Just a couple. For those that do, are you doing MPEG-2, MPEG-4 AVC, HEVC? What are you using? MPEG-4. So MPEG-4 AVC, one of the data fields in there is known as an SEI message. It's what carries all your metadata. What I mean by metadata in this case is that's how you carry things through the compressed bit streams, like closed captions, active format description, time codes. All that's carried as metadata in that through the SEI messages. Okay? If you don't know what that is, don't worry about it. So those are the static systems, but that's not real world. Things change. What if you needed to change your function of what was dark, mid, and light to more accurately display what was being captured at the scene on every video frame? Now you have dynamic metadata, and these are dynamic HDR systems. Okay, these different systems are described in another SMPTE standard, 2094, content-dependent metadata for color transformation. It specifies deep shadow, midtones, and highlights again, but instead of it being a static one that doesn't change for a scene or for the entire episodic or motion picture, it could change as much as every frame. So you absolutely have to have it. Great, let's just do this. It's very hard to get metadata through your plant to the right device. So it's the right way to go. It's a bit difficult to do that. But guess what? Because it was more difficult, that's an area that is ripe for intellectual property. We do it better than you do. Oh, let's have a standard. Let's all go to the standards body and see which way it's going to be done. And we'll all work it out with a grand alliance and live happily ever after. Except it didn't happen. So the three most popular, actually I won't even call them most popular, the three that are most forced down our throats, HDR systems, are known as Dolby Vision, Samsung HDR10 Plus, clever name, it's HDR10 plus additional metadata, clever. I wonder who their marketing department is. Then we get the opposite. We have engineers at Philips and Technicolor that clearly run their marketing department because they have a completely impronounceable name for theirs. It's called SLHDR1. So clearly they're not trying to sell the consumer for that, right? Not only that, SLHDR1 stands for single layer, high dynamic range type 1, except it's not a single layer. So it's actually dual layer. Okay, I'll get off my soapbox again. I lived through this stuff the last 3 years. I'm on the standards body. So this has been, shall we say, the old Chinese proverb, may you live in interesting times. It was really, everybody got a trophy. Everybody's happy whether they participated or not. It has caused an absolute nightmare. So when you guys are ready to do HDR, it is going to be a little bit of work to figure out which HDR system you want to use. All I can recommend to start with is keep it as simple as possible to start with. And as the industry matures, this will flush itself out. As a matter of fact, it's already starting to happen. At this point in time, except for one major television, there's tons of TV manufacturers across the world, but I think we all know there's probably less than a half a dozen that are really the major brands, right? Okay, we know who they are. But all but one major brand has implemented Dolby Vision now. So if you have a Dolby Vision content in dynamic, right, everybody does HDR10, by the way. These other ones here on the older slide, oops, wrong way. Everybody does these because they're simple, okay? But people want better HDR experience, so they want to go dynamic, okay? So they want to go dynamic. If everybody implements it, then we have a de facto standard, but not everybody does. So every major television manufacturer except one implements Dolby Vision. Can you guess which television manufacturer, it's a major world television, doesn't implement Dolby Vision? Can you guess? Mm-hmm. Yeah, who do you think it is? Samsung. Yeah, very good. Why? Well, I think you figured it out. I don't know if this is going to be forever, but that's where they are right now. The reason Samsung developed HDR10 Plus, or at least they tell us the reason they did it. This is not publicized to consumers. This is for us. And the standards body says, how does Dolby make money? Dolby doesn't build stuff. Well, they build theaters. If you ever get lucky enough to see a Dolby reference theater, I don't know if you have any in Argentina. Go look it up. It is unbelievable. I have the pleasure of knowing so many people at Dolby. I'm in San Francisco a lot. And so I've seen probably at least a half a dozen movies in the Dolby reference theater at Dolby, which is Atmos sound. So the sound is just absolutely incredible. Okay. Anybody see the new Queen movie?
Yeah.
Okay. Can you imagine the soundtrack to that in the Dolby reference theater? It's mind blowing. It was just absolutely a phenomenal movie anyway. But that just, you're there for this, and it's just, you felt like you're at the concert. Okay. But in addition, it's a Dolby Vision theater, so it's all in high dynamic range. So they had a version of Bohemian Rhapsody done for that Dolby record that was mastered for that display, okay, and in Dolby Atmos. It's mind-blowingly amazing to see a movie that way. Then you go to a regular theater and you're like, you know, unless you go to an IMAX. IMAX is cool. So, but I digress. Anyway, Samsung developed it because Dolby makes money through licensing. Licensing is royalties, and people don't want to pay royalties. I'm not representing a position of MediaKind when I say that I'm trying to impart to you technology information. It's an issue with people playing the role. It's a commercial issue. MediaKind has no position on that. This is just me telling you information, okay? So they offer this. Now, some companies out there like that. In the case of Amazon, at least in the US, Amazon Prime offers some HDR movies. They're done in HDR10 Plus because Amazon didn't want to pay the Dolby licensing. Problem is, very few sets do HDR10 Plus. So what happens is, if you do HDR10 Plus on a set that doesn't do it, it reverts back to HDR10. So you still get HDR, but it's not as dynamic. So it will still look great compared to SDR, don't get me wrong. But it's like the difference between a low-end home theater system and a high-end home theater system. The low-end one still sounds much better than the sound that comes out of your TV speakers, right? But it doesn't sound like a high-end one does. Sort of like coffee machines, right? You can make yourself a, you know, a $2 cup of coffee, or you can have these fancy Nespresso machines, which I had the pleasure of having one this morning because Roberto made me a nice espresso this morning, is the best, right? Or you could go with those $5,000, grind your own individual one. You get an 1/8 of an inch more of crema at the top. And you go, oh, this is great. But like engineering, it's the 80-20 curve. You get 80% of the benefit, and then it costs you so much more to get a little more. It's the same thing here. So the jury's out on this, whether how successful it's be. This one here was designed, it's very interesting. The color mapping, the dynamics of these systems are all good. Actually, Dolby's and Philips Technicolor have a better dynamic system than Samsung does. So it's not that there's something wrong with it. It's just that it gets too complicated. Here's a case in point. Great idea on paper, really good engineering, not so much in the actual practical part of it. The point of SL-HDR1 was to come up with a backwards compatible format so you could have one stream delivered out there into a TV that doesn't understand HDR, it will display correctly as SDR, and a TV that understands HDR will display it as HDR with a single stream. Sounds fantastic, doesn't it? Yeah, except it's not truly backwards compatible. Plus, in order to implement it, you have to have their intellectual property in the HDR set, and not everybody is implementing it. But the bigger problem for me is it produces a fantastic SDR stream from a native HDR stream. Does that sound like the wave of the future to you? You're going to hamper all future systems based on what we're doing today. It's backwards. Again, that's Matthew Goldman's opinion, not that of MediaKind. I'm just letting you know. This is why we have such a quandary out there right now, because there's at least 6 different systems, and there's actually an SL-HDR2, which is, ooh, we can also do it their way too, start with HDR and come up with an SDR color volume mapping function, right? So it's way too much stuff. The big difference here is the metadata that you have for Dolby Vision and for Samsung is the same type of metadata that you have for the static stuff. It's the same type like you have for active format description. I want to say this again, it's very important distinction. This is not signaling to tell you what you do. This is telling you what you have. The device can make its own decisions, but it uses that data to help it make the better decision. In these cases, it's the same here. You don't need to use the Dolby Vision as a slight. You don't need to use the Dolby Vision metadata to recover HDR from a Dolby Vision signal. But I'll tell you, a TV set that doesn't understand it's going to have a very hard time recovering that because it's changing every frame. That's a lot. Yes?
Actually, who's making the decisions to create that metadata? Is it a colorist? Is it an automatic lead on the?
It's actually both. It depends on the system. If it's a production that's offline, oh, do you need me to repeat the question? Or did you hear it? Okay. who's making the decision of how the metadata is done? If it's an offline production, like an episodic television series or anything you're producing for later viewing, the decision is made by the colorist. Color is still very important here, and it's really pristine. They will frame by frame, like the comment I heard, I had the pleasure of meeting James Cameron at one of the Simply functions we had a couple of years ago, and he was telling me that for Avatar, he literally himself, which is very unusual, was so concerned about the look of Avatar that he sat in a seat. They had this area around, they had the reference studio when they were producing it. And he had a seat that was sat up behind the colorists. They actually had two colorists in front and Jim Cameron was behind. Every frame. The movie's 2.5 hours long. Okay, there are 24 frames per second. How many seconds are in an hour? How many frames is that? It took them a year to grade that movie. Every frame, they bid it, and then they go to the next frame, and they go, oh, wait a minute, I don't like the way this looks now. Let's go back and regrade the previous picture. Okay, that's how pristine a colorist can make it, and I don't know. Whether you like the story of Avatar or not, you cannot deny that the cinematic effect of Avatar is just simply amazing. It was a beautiful film, right? If you're into that stuff, I am, so. But you can see the painstaking work that nobody sees do that. That's unassault. When you go and you're doing a live event, Dolby Vision has a version of it called Dolby Vision Live, and it's an automatic machine. It's called a I forget what it's called now. It might be called CMS, color mapping system. That's not it, but it's something similar to that. It tries to make the choices for you in real time, live. Now you can still tweak it, but as you know, live is live. So there's no, oops, I didn't like the way that looked. Hold it, stop playing the game. I need to fix my health. Yeah, you're not going to be able to do that, right? So anyway, that answers your question. The difference with this and SLHDR1 is because it has converted the pristine HDR into SDR using a proprietary, I mean, they're going to say it's not proprietary, it's defined in this ETSI standard. Yeah. You know what an ETSI standard is here? This is European Telecommunications Standards. It didn't get done through CENTI. What it is they brought it in and said, here's what we have. Anybody have comments on it in the world? Anybody? Anybody? Okay, good. Boom, it's a standard. Okay? It's you can build off of it, which is what a standards document is for, right? Believe me, there's a picture of me in the Philips and Technicolor's lab on a dartboard. My photo's on there, okay? Because they know that I'm not a big lover of their solution. I think it's, as an engineer, I find it appalling how they did this. It's just, it doesn't match my worldview of how you do engineering. What's the benefit to people? This is the benefit to them. It's not a benefit to society. But because you're using their system, in order to recover it, it is actually prescriptive, not descriptive. By prescriptive, you have to follow what the metadata says to recover the native HDR, because you're doing the inverse function. So if you don't understand that inverse function, what are you going to show on your HDR TV? SDR, right? My wife trying to reach me. She knows I'm presenting now too. So. Anyway, so it's required to recover that signal. So how do we know what we're carrying in the stream? This is why I talked about this. There's signaling this metadata. How do we know what we're carrying it through the bit stream? So here's the camera here, and you know when you have the front haul, the contribution feed, right? Excuse me, the back haul, contribution feed, and then you bring it out to the distribution. Then the distribution is the front haul or delivery, primary distribution to the delivery area, whether it's a cable head end or broadcast facility or an internet service provider, right? The emissions are going out. You have to carry the HDR signaling, which signaling tells you what you have for basics. It's not giving you information like metadata, because it's just saying this is HDR and this is the format. This is very basic information. It's signaling what you have. The metadata is the actual data itself that you would use as a hint to how to recover the other end. So, wait a minute, did I go too fast? No. Sorry. Okay. We all know what SDI is, right?
Yeah.
All right. So SDI, and we also have, it's an industry-specific interface. No other industry uses it, defined by SMPTE. We start at the copper or the glass level. We do a data link on that framing, right? And we have a networking layer, and then you have the transport, and you have the data on top of that, right? And bear with me 1 second here. I should have had the top off this, I did not. Because I'm yapping too much. Okay. So there's HD, there's 3G, there's 12G, 12 gigabits HD, right? Or there's a combination of 4 3G ones working together, that's another standard, right? Or, oh geez, what about stereoscopic? Remember 3D? Not very popular now, but you still have to describe what's left and right. That's another set of standards. Oh, some use fiber and some use copper. Well, that's a different standard. So there's 3 dozen different SDI standards. Also, are you familiar with SDI over IP? SMPTE standard 2022? Have we done that? Okay. So that's when you wrap SDI framing into IP. So signaling is carried in the SDI, so therefore because it's SDI and IP, it's the same way, in something known as a payload ID. Now, for those that understand SDI, you know that in the preamble in your front, you have between end of active video and start of active video, you have the HANTs and the VANTs, the vertical and horizontal ancillary data, which used to be used in analog before that, but now it's used for data fields. In there, you also have a place as part of that where you can put the payload ID. The payload ID is a 4-byte field that you can now tell it whether it's SDR, HDR, wide color gamut, narrow color gamut, right? Which form this is, okay? That's carried in, and that's another SMPTE standard, 352. And this is telling you some examples of where they're carried. Here's 4 different, of the 3 dozen, here's 4 different standards. The metadata is carried by a brand new SMPTE standard. It got published last year. It's known as 2108, but it didn't invent a new mechanism. It's just telling you how to carry it. It's using the venerable 291 data space. That's where you carry, again, whether it's audio, it's in HANTs, or in VANTs, or VANC, maybe you call them Hank and VANC. That's where you carry things like closed captions, right? Active format description, your time codes, a whole bunch of other stuff that gets carried in there. Content advisory codes, things like that. They're all in that. This is using the same areas. It's just a new standard because it's telling you where to put it, right? If you're doing production, I don't know how many people here do MXF for production. There's a key length value, a KLV version of it, which is just a different one. It's the same thing. There's a place to carry it in the midstream. Now, how many here are familiar with the new professional media over IP standard, SMPTE standard 2110? A couple of you. Well, I'm going to have a whole session on that in the later session. But anyway, there's a different way of transporting it in a 2110-40 stream, which we'll talk about when I get there. But the point is, it's well known where this stuff is and how to carry it, but you have to follow that. And most of the equipment that's out there now does this. Some of the stuff is new because it's newly defined. In the case of consumer stuff, like this TV here, what do I have plugged into my laptop that's working this display here? This is HDMI. So just like SDI is to professional media, HDMI is to consumer media. Well, you have to, it's brand new, so you have to carry the same information to get to the display. So you have to have a minimum HDMI 2.0B. So if you have something that's not 2.0 as your HDMI cable, there's nothing you can do about it. You have to get upgraded. So the old ones couldn't support the bandwidth. But A and B versions of this, those are firmware blastable. If you have a connected television that has HDMI 2.0, you can download the firmware to your TV and actually upgrade it to support all these different HDR formats. So that's cool, right? But it has to be a newer TV that has HDMI 2.0. And then for those that do compression, it's a signaling is carried in what is known, whether it's ABC, which would be for HD, up to HD only, or HEVC, the new standard, which does 4K. 4K encoding uses HEVC, high efficiency video coding. I'm going to talk about a little bit more about that in a later session. AVC only goes up to HD, but they both have something known as a VUI, video usability information. That's where the signaling is carried in the bit stream. If you don't know what that is, don't worry about it. Just know that that's the place to carry it. And for those that do know, it has the SCI messages again, the supplemental enhancement information messages. That's where the metadata is carried in the stream. So again, the important thing is, if you know what I'm talking about, now you know where it is. If you don't know what I'm talking about, at least you know there's a place where it gets carried in the bit stream. And when it comes time that you'll start looking up this stuff, you at least know that it's somewhere in that. Now, here's the great news. Just like the different systems have incompatible metadata and transfer functions, I just thought, let's just make it a complete trifecta, and let's have completely incompatible SEI messages too. We did it. Woo-hoo. They're all different. Fantastic. Good job, industry. Okay. So now, I'm trying to make it funny, but it actually isn't funny. But because HDR is just such a fantastic technology that if they had just picked one system, a lot more people would have it on the air right now. It's because it really is that good. All right. Remember back in the old days when we were all doing standard definition, we first introduced high definition television. Fantastic. So we're going to broadcast a brand new high definition television channel, but we're new. So most of our content was still in SD, or your commercials, your interstitials, right? They were in SD because it's a library of it. All your news clips or your sports clips, and you're in a news or sports news show, they're all in SD. But you had an HD channel. That's all right. When the main content is HD, we'll send out HD. And when the interstitial comes on for the commercial, we'll just send it out as SD and TV will fix it. Or the same thing when you're doing a show. Does anybody remember what happened when people first started doing this 20 years ago? What happened when you sent an SD signal to an HD TV? Do you remember?
Yeah, it was horrible.
Yeah,
Horrible.
it was horrible because every TV manufacturer did it differently. Some were pretty good. Only after 3 or 4 seconds of the picture looked pretty good. Some eventually would do it, you know, but it didn't look bad. It just was the wrong format until it switched over. Other ones, if you can believe this, hung and never came out. It stuck on a picture. They didn't know what to do with it. That's not exactly a good consumer experience. And if you're a service provider or a content provider, who are they going to call? They're going to call the TV set manufacturer? No. They're going to call up whoever they're paying for their TV service and say, your stuff broke my TV. So what are you going to do as a content or service provider? You're going to make it look good. So you needed to pre-convert the streams. So what we did a lot was we converted SD to HD. Now you can't invent resolution, right? But you can make SD look right on an HD display by mapping the smaller pixels into, you line doubling, quadrupling, or you just leave it alone, but make it look like it's HD, use HD signaling. So the TV's not switching signaling. As far as the TV's concerned, it's all HD, but when it shows the SD commercial, what is it showing? A lower resolution that's showing it correctly. The reason I walk through this is we have the same problem with HDR, right? On an HDR TV, if you feed it SDR, they all act differently. So the right thing to do is you do what? You color volume map the SDR into HDR, and you do it in a smart way. And you need to do it in real time. And the mapping process is called inverse tone mapping. Remember I told you it's tone mapping when you're doing the color volume changing, but going from a smaller volume to a larger one and making that up, that's inverse, get it backwards. And because it's in real time, it's real time. And because we're going to be smart about it, it's real-time intelligent inverse tone mapping. People said it couldn't be done, it can be done. For instance, MediaKind, we offer a real-time intelligent inverse tone mapper. Other people do as well, okay? You can't create HDR from SDR, but you can balance it. Think of it this way. Remember SDR had that smaller color volume? If I just took that SDR color volume and sent it to an HDR display, depending on the mode the TV is in, it will do one of two things. It'll be so stark on the display that you can't see anything that well. It'll definitely look wrong. Or it'll be so bright that everything will be washed out like pastel colors. In either case, it doesn't look right. Assuming it doesn't hang the TV to begin with, right? When you map it, think of that smaller color volume. You're going to take that and do what? An EETF on it. You're going to map the bit streams from one, so that that smaller color volume is in the right place within the larger one, so that when you display it, it will still be SDR. You won't get a huge dynamic range difference, right? but it'll be in the midtones, it'll be in the right place in that, so it'll look right as SDR, but on your HDR display. Does that make sense? So that's what I mean by color mapping. Now, this is what it looks like. Now, again, you have to bear with me, because this is what? This is a SDR display and a narrow color camera display, right? So I'm gonna emulate it. I'm the master of fake imagery. Okay. So I know I show these as individual frames, but think of this as a sequence, right? Here's your main content, it's football. You got left and right is football. And I have two interstitials coming up in between. Each one's probably a 30-second spot. This is in HDR. Okay, when I say HDR here, I mean HDR, WCG, 10-bit, okay? So is that. The interstitials are in SDR. They're probably 8-bit and they're probably narrow color gamut as well, okay? So we show it through. Now, because we're gonna assume this device doesn't have any problem displaying it, this is what it looks like. It doesn't look that bad, it's just SDR, it won't have that dynamic range, right? Here's the problem. Even if it shows it on the display and you don't have that gross too dark or too light condition, this is what it's supposed to look like. It's still SDR. This is nice HDR, it's still SDR, but there's no hue changes. There's no problems with the midtones. This is hugely different. You have an advertiser. I'm not representing Coca-Cola here. This is called Matthew being lazy, going on the internet and grabbing a photo he can find to prove his point, okay? It's a good point though. I hope you at least realize that Coca-Cola and companies like Coke, doesn't matter if it's Coke or not, they spend a lot of money on branding. There's a Coca-Cola script. That is their script. That's their font. Nobody else uses that. That font is called Coca-Cola font. It's theirs, right? We have a whole alphabet of it. We've only seen Coca-Cola, right? The other thing is they have Coca-Cola Red. That's their color. That's their brand. It's the script and the color. If you show it as that, and they're paying you, you know, $20,000, $50,000 for that spot, do you think they're going to be happy with you? They're going to ask you to do what? Make good. If you do this all day long, that's a lot of make goods. This is why it's important. Look at the skin tone. Here you can tell. You can see her face. You can't see that. Without seeing this, it looked fine, right? But when you see what it's supposed to look like, I hope I've made my point here for doing that. Now, one of the last topics here is, remember we talked about viewing distance, right? What we didn't talk about is the fact that, and I hope this makes sense to you, since 4K is 4 times the resolution of HD, in the uncompressed domain, if it's just a digital bit stream, you would expect what? That it takes 4 times the bandwidth, right? So it takes 4 times the bandwidth to transmit. So if you have full HD, it's 3 gigabits per second. So it's 3G SDI. If you use in 720p or 1080i, it's 1.5 gigs. So let's just talk about full HD, it's 3 gigs. If you're doing 4K, it is therefore 12 gig SDI, or 3G SDIs working in concert. It's a lot of bandwidth, not just in transmission and around your studio, your delivery, but also for storage. Even in the compressed domain, I don't care what pick your favorite compression standard, it takes up more. It's typically somewhere between 200 and 250% more bits. It's not 400%, it's not 4 times, but it still takes more bits to do 4K versus HD. It's more information. The cool thing is, to do HDR, one versus the other, it's really not that much more bits. Yes, 8-bit to 10-bit, right? You're gonna have 20% more bits. But if you know anything about how compression works, what is compression recording? How you start with a baseline picture. I'm really simplifying the process, but just to explain it to you. You've recorded one picture and you've compressed it, but you have that master picture now. The next frame of video, you compare against the previous frame. And the reason it's called compression is, what are you actually sending in the next frame? You're not sending the whole frame again, you're sending what? The differences, the changes, the residual, okay? The better match you get between the two, if it's the exact same frame, like it's a still image, it should be an extremely low bit stream, like almost nothing. All you're saying is same as last, right? If there's a slight difference, you're just sending that small residual. Well, guess what? If your master SDI version is 10-bit, that's your main one, but your output you're recording for consumers is 8-bit. When you then decode that 8-bit one from your impression and then feed it back in, and now your master is the next 10-bit frame, you're going to get an error converting from 8-bit to 10 bits, right? So there's an error there. So you're going to code that error difference because the consumer's seeing the 8-bit version, but the one that you're comparing it to is your master, which is 10-bit. That produces a residual error. But if your output stream is using the new 10-bit format, you don't get that error. So you have less residual. As it happens to turn out, on average, over a feature, whether it's a movie or episodic or whatever, it turns out that the gain you get by staying with 10 bits pretty much overcomes the extra residual you have to add to the stream by adding 10 bits to it at the beginning. You're trading one off for the other. So it actually doesn't really gain that much, maybe 5%. It's very small. So the good news is HDR, which is just light, it's just different values, doesn't really cost you anything more to do it. But 4K to HD costs you a lot of bits. So I'm very clever. I've been talking about this for 3 years now. The best bang for the bit then is to do HD with HDR, right? Oh my God, but there's no such thing as a 1080p HDR display out there. That stinks. Not really. If it's 1080p, so it's a progressive screen, all the new televisions that are 4K, every single one of them have up converters built in. In the old days, you had to buy this big external box for home theater, remember? The up converter for your big screen because you had your little SD picture, which looked great on TV that's this big. Didn't look so good in your home theater projector screen, right? So you line double and quadrupled it and then interpolated between the lines to smooth it, right? It's still the same resolution, but it looks smoother, right? The new TVs, that can be done in a tiny little spot inside one chip. It's so irrelevant, it can do it in real time. As long as it's progressive, that 1080p. Sometimes deinterlacing to do it is not so good, but the other stuff is fine. So if you transmit in 1080p and you don't convert it to 4K, the TV can do it in real time, no problem. Yes, Matthew, but it's not really 4K, just like SDR to HDR is not really HDR, just like SD to HD wasn't really HD. What did I teach you earlier? If you're sitting 2.5 meters or 3 meters away from your TV set and it's this big, are you looking at 4K or are you looking at HD? So yes, it is a difference, and I'm not trying to downplay 4K, but is that difference worth the bandwidth that you're required to use to get it out there? You might not have bandwidth to carry 4K, but I can tell you right now, if you're broadcasting in 1080i or 720p in SDR, and you want to use almost the same bandwidth, but in the new TVs, I'm ignoring the fact that it's not backwards compatible for the purposes of this discussion. It's not. But let's just say you want to offer this new service because it's so compelling. HDR is so compelling that if you did 1080p HDR, it would make a huge difference to your consumers, assuming your customers, of course, have a 4K HDR set. There's no 1080p HDR set, but this gets up converted to it. Looks great. Best bang for the bit. Yes?
It looks like there's a lot of displays that do not have the necessary needs and to show real HDR out there, but they are 4K, right? That's what they're trying to sell. Yeah,
the first generation of 4K sets were SDR only.
Mm-hmm.
Worse, they were SDR only and HDR didn't exist. The good news is that was only for a few years. The new sets that are SDR only, they are SDR only, but they understand HDR, the signaling for it. They just can't display it. So what do? They read the metadata and they, come on guys, they do color volume mapping down to SDR. So they take the HDR and they can make it SDR because they understand the new signaling. So that's the good news. Now what you really want to do is, in a few years, you're not going to be able to buy an SDR set. It's just not going to be able to. It's like, it's very hard to buy any TV over, say, 40 inches now and have it not be 4K. Because the cost to run 2 production lines is too much money, so they might as well just give you the 4K. Even if everything you watch on it is HD. Okay? Sometimes they're so good that if you have not very nice looking HD material, they'll actually clean it up. I mean, it's done through filtering and stuff. It's not, again, not 4K, but it actually makes your HD look better, even though it's HD, unless the upconvert's done right. I hope this made sense, of course, for this. Any questions before I move on to the next section? This is question time. We have one student. I do not give trophies to everybody. Okay? Any other? No, in all seriousness. Was that good? Was that helpful? Okay. Now, I should probably do this only because someone pays me to be here. We make all this stuff, but that wasn't the purpose of my explaining to you. My purpose was for you to understand the technology. Hopefully you'll look to MediaKind, but I'm not here to sell products. I'm here to have you understand the technology. Go ahead.
Yes. What do you recommend when you have to convert from SDR to HDR using HLG or PQ10? What do you recommend?
Well,
in terms of
the biggest thing when you're going from SDR to HDR like that is to have a good real-time intelligent inverse tone mapping. And there's probably at least a half a dozen companies that make that, including ourselves, for that. So we build it in. You can't buy it with us. You can't buy it as a separate device. If you go to a company, I'm not sure who offers this. I'm assuming Snell was just bought by Belden, right? Okay. So, but Snell, I think, still sells a professional product that will do that in real time. Grass Valley might have one. If you're going to encode it using our MPEG-4 or HEVC encoders, we'll do that conversion process for you in real time.
But I refer not in terms of brand, in terms of solution.
Oh, if it's,
using
it doesn't matter. We'll do
HLG.
PQ or HLG. We'll do them both in real time. This makes no difference to us. Let's back up the question a little bit more. If you're running a live production now, so let's take your question and if I may, let's word it a little bit differently. You're worried about a very specific case, which is SDR to HDR. If you worry about the more general case, if I'm doing a live production, what's easier to use, the PQ curve or the HLG curve? I think I mentioned earlier, today, right now, to get an end-to-end production working, it's easier to do HLG.
Yeah.
I don't know if this is going to be true in 2 or 3 years. I can tell you that's the only place where HLG is being used because it makes it easier. If you're doing, if you're producing original content at the television episodics or a motion picture, it's universally PQ because it more closely matches the human visual system, and you have a colorist who's going to be doing that. HLG is a guy in the field going, I just need to get a picture that looks good going out. So it does absolutely, I know I'm being kind of off the cuff funny. I don't want to be labeled that. HLG is a very good system. I don't personally believe it's as good as PQ as far as absolute quality is concerned, but regarding convenience, it is just so much easier to use today that's why people are using it. There's an issue to me when depending on light levels, because HLG today, the way it's done, is they're making a statement that everything's 1,000 nits, and I just know everything's not 1,000 nits. The displays aren't that anymore. They made this decision when the TVs were 1,000. Oh, I skipped the piece earlier, I should tell you. I talked about LCD displays being the peak white levels being 1,000 on most of them and 2,000 on the really better consumer sets. I forgot to mention OLEDs, organic LEDs. So an LCD, you know how an LCD display works, right? LCDs, the technologies, when you apply a voltage to it, right, it puts a block on the pixel. It's like a shutter. It's an electronic shutter. It actually, it turns opaque. When you take the voltage away, or I might have that backwards. One or the other, doesn't matter for the purpose of this. When you take it away, it's clear. It might be when you apply the voltage, it's clear, but run with me. Okay, so it's a emissive technology. The light in behind it has to be there for you to see light, and then you're blocking that light. So what does that tell you? You're never going to get really good blacks with LCDs because you're blocking light if there's a light behind it, right? OLEDs, when you're supposed to be black, what is it? It's off. So it's black. Now, it's not as bad as it used to be because the new TVs that are out there use what they call regional background lighting. They no longer use fluorescent tubes. You know, if you go back 20 years ago, LCD sets use fluorescent tubes behind them. Now they use LEDs. They're not using LEDs to display. It's not emissive, right? They're using LEDs to light the background. But because of that, they can now turn them off in groups. So if you're in a dark area of the screen, they can shut off a small area of lights and use other lights around them, so that even when the light's fully on, instead of being as bright, it will be dimmer, but there'll be some light, and they can control the amount of light. So actually their black levels have dropped now, and they look pretty good. The reason I'm telling you all this is because an OLED set has fantastic blacks. Here's the problem though. It's a lot easier with an LED and an LCD set to get really bright. Just turn it up. If you're an OLED, the organic LED, you have to do light and color. So it can't get as bright. So the peak white level of a typical HDR OLED TV now is about 700 to 800 nits, where on an LCD it's 2000. But here's the thing, it means that, and if you've seen pictures of an OLED, you know the colors look beautiful. Even your cell phones that use AMOLED displays, they're just beautiful colors. I mean, it's absolutely fantastic. But what do you need to do though? Yes, you have to be in a dark room. So if you love an OLED set, and you can put it in a room in your house where there's not this, where there's no windows, that's the way to go, at least today. Now, they also have these new TVs that are using quantum dots or quantum crystalline structures that are getting a little bit better in brightness and color on that. So the technologies aren't over yet. In some places, we're actually using crystal LEDs now. It's a long story, but the point is TVs are getting much better now. But remember, it's about dynamic range. So if your room is dark, you can get using an OLED set. Beautiful, because the dynamic range on them, although we used to call it contrast level, is huge difference for that. Okay, I forgot to tell you that earlier for HDR. Anything else on HDR or 4K viewing distance? I didn't talk at all about higher frame rate. They're also looking at higher frame rate. Why do you need higher frame rate? Because you get motion judder. But I'm not seeing motion judder now. It's because you're sitting at a distance of HD, which means the TV set only fills up 1/3 of your central field of vision. So an image is moving across your screen and it's doing this. But with 4K, if you're sitting at the right distance, it fills up 2/3 of your central field. So now the image is doing this across you. So any motion judder, you'll see more. So they want to, for high motion things like sports, they want to double the frame rate. Double the frame rate, it also introduces all of a bunch of issues too, but that is the way it's going. So the stuff, if you're in a 50 hertz country, they're talking about doing 2160p 100 or 1080p 100 right now for sports. Not talking heads, it makes no difference, right? If you're a newscast, but if you're doing like auto racing, horse racing, football, it makes a huge difference. It looks great. In the US, where basketball is very, very popular, where they shoot basketball and they follow the player. If you're in a big TV, you can see the legs doing this. You see a lot of motion judder. So, and I think that's it on that one. So, I'm not seeing any more questions. Sorry, I'm not done yet, and I am late, but I hope you guys can go through this. I'll try to go a little faster on this part because I'm basically supposed to be out of time on my session. I haven't started it yet. But you guys are so interested in the other one. So, it's time for a new codec. How many people here use MPEG-4 AVC? Pretty good stuff, right? But it's 15 years old now. And you know, again, what you're trying to do all the time is for consumer stuff, is get the lowest possible bit rate for the highest picture quality. If we go back 20 years ago and you were doing content over the top, the bandwidth was so low that the pictures didn't look that good at all compared to broadcast TV. Now you know with MPEG-4 AVC, and a nice internet connection, you can actually get pretty good pictures. But it's 15 years old. The good news, it has almost universal reach now. Pretty much, unless your set-top box is really old, every set-top box, every smart TV, which is the IDTV, pretty much all, of course, the new smartphones and tablets, they all do MPEG-4 AVC now, right? So, but we want to do something better. So the questions I get asked a lot are, what about these new codecs, HEVC and AV1? They promise to be half the bit rate for the same picture quality of AVC. Why hasn't HEVC? It's been out for a few years. Why hasn't it replaced AVC? And can I even commercially deploy AV1? Have you guys even heard of AV1? AV1 is been championed by Google as a royalty-free codec. We don't know if it's truly royalty-free, but you understand that people remember the same problem we had with Dolby Vision, people don't want to pay for it, so they like royalty-free. Again, this is not MediaKind's position, I'm just telling you what the industry's doing. So I'm gonna go a little bit faster this section because I'm out of time. But the difficulty is, in the early days, you go back to 2003 and 4, there's a cost, there's a royalty you pay for use of MPEG-4 and it was controversial because they had a contributory fee you had to do. But since 2004, almost every single set-top box, radio, TV, smartphone, reaches it, browses, everybody does this. But it does cost a little bit of money. But at least it's understood what you pay for it, and if you're internet streaming it, there's no royalty. It was deliberately done that way. Okay? HEVC, even though it's been out for 2 or 3 years now, the licensing is a complete mess. There's at least 3 different licensing patent pools that say they have essential patents. And there's a boatload of, I don't know if boatload translates to Argentinian Spanish here, but there's a lot of, that's an idiom, it's a US idiom. There's a lot of, try not to talk in idioms, but there's a lot of different companies that have essential patents that are in the pool. So it makes it difficult to use. So how do you, for backhauls and front hauls, no big deal. Pretty much everybody has agreed to no royalties. But if you're going to be delivering to an end user, if you don't know the terms what you're delivering, you don't know what you owe, maybe they'll let you get away with it for a couple of years, but at some point in time, someone's going to come knocking on your door looking for a royalty. So it's held it up. By the way, that's what happened to ABC 10, 15 years ago. How many people remember SMPTE VC1 or Windows Media 9? It was becoming popular because it didn't have these problems. This is like deja vu all over again, right? It's the same problem. It's only in about 15% of browsers. Google won't support it for their main alphabet because they want it for free. They don't want to pay for open standards, and they've done it. But not everybody supports that, okay? And you're going to get the slides because I have web pages for you to look at on here. AV1, which is the AOM, I forget what it stands for now, Advanced Open Media Alliance, Alliance for Open Media or something. What's AOM stand for? Alliance for Open? Anyways, if you've heard of VP8, VP9, this is what VP10 was going to be, except now they call it AV1. And it's not just Google, it's Cisco, there's a few other companies that are involved with it, trying to do a royalty-free reciprocal license for it. And obviously for browsers, because Google and a few other people, it's in a lot more of them. But it's not, it's everything software decode because chipsets aren't available yet. They will be. So this is starting to get confusing. Which one are we going to use moving forward? Well, we are one of very few companies that still has a major research firm in the compression. So we did testing in our own labs of AV1 versus HEVC. Because we didn't know what to do. We're not trying to be, we don't, for us, you know the old expression, if you make guns, you're an arms dealer, you sell to both sides, right? The same thing, it doesn't matter to us. We make MPEG-4, we make MPEG-2 encoders still. We make HEVC encoders, and if someone wants to buy an AV1 encoder from us, we'll make that as well. But we wanted to know, is the stuff that you're reading on the web true or not? Because if you go on the web, there's a whole group of people that are saying, oh, AV1 is much better than HEVC. And there's a whole other paper who said, now that's flawed science. It's actually much worse. So who's telling the truth? One of the problems is it's incredibly difficult to compare codecs because you have to use the same conditions to compare them. So what we did is we went right back to the reference models and then simulated that in our lab. That's really the only fair way to do it. You can't do it against our device, because it'll give an unfair advantage. Our device does it much faster, right? Because we're not using software, we're actually, we do it in hardware. So at the end of the day, there's detailed stuff in here. There's a white paper that we presented at the SMPTE Annual Tech Conference in Las Vegas last October, called this, so you can get, you might have to pay for it from SMPTE, but I'm sure it's a small amount of money. But at the end of the day, we did actually show that in the comparison that we did show that AV1 was about 10% better, more efficient pitch quality. But here's the catch. It was 72 times slower for us to encode it. So that's okay if you're offline producing it and you have the time. That doesn't sound like live encoding to me. So remember, it's application driven, but it's allegedly free, right? So we'll see. And these are different stuff for it. So where do they differ? Okay, now this is a different PQ. Unfortunately, in our industry, like everybody else, ever heard of TLA? A 3-letter acronym? TLA, get it? 3-letter acronym. Anyways, people reuse things. So this is not perceptual quantization here. This is picture quality. PQ has been used for picture quality for 50 years. PQ for HDR has been for 3, right? It's an unfortunate reuse. But what we find is, even though it's 10% better, we don't believe consumers will actually notice any difference at all. We think they'll find them both about the same. And it all depends on consumer reaction. So we can go through this in more detail when you read it, but the point is, by looking at certain aspects of the sequences, you can see differences. As a general rule, AV1 pictures are more blurry and softer than HEVC ones, which are more sharper, but they're also more blocky and have more ringing. Do you know what ringing is in a compression artifact? That's when an object moves, and when you see them move, it looks like they have halos around their head or around the arms. That's ringing. That's a compression artifact. Most people that view professional quality video regularly, like me, we prefer sharp pictures, just like I prefer HDR, with an acceptable amount of artifacts of blocking or ringing, instead of having the picture be so soft that it's not even HD. They'll call it HD, they'll call it 4K, but there's no high frequency information. That's why it's soft, it's been taken away. But a lot of consumers don't like the blocking of the ringing, they like something to be really clean, so it'll be clean and soft. So I just want to tell you that they both are good, where they have failures or in different ways, so it comes down to personal preference. And for 10%, it's not worth changing from one thing to another. So you pick your favorite and go with it. Now, MPEG-2 was published in 1994, AVC in 2003, 2004, depending on the version of it. HEVC was 2013. There's 10 years difference between them. And when you went from MPEG-2 to AVC, it was basically a 50% bitrate reduction for about the same picture quality. Same thing from AVC to HEVC, 50%. When you go just a few years later with AV1 to 2019, it's been about 5 years, it is better, but it's only about 10% better. So if you're greenfield, you pick the one you want to use. If you haven't done anything, do you know what greenfield means? I'm sorry, I just used another idiom, sorry. Okay. So if you don't have anything to implement, you're starting from brand new, you pick the codec you want to use. So if you don't want to pay royalties, you can pick AV1. But if you want an international standard, you pick HEVC. It's your choice. You'll get a little bit better. Remember, it's 72 times slower. But that's the thing. When you went from MPEG-2 to AVC, decoding was twice as long, encoding was 8 times as much. But you had 10 years later. What happened in 10 years? 5 generations of Moore's Law. So processors were much faster, or more cores were working on it. So this isn't a problem. Same thing here. The problem is it's only been a few years and it's 72 times more. Not in the decoder, it's fine. So the jury's out whether you can use this or not, okay? At the end of the day, in commercial encoders, we're trying to sell you something. It's always been a trade-off between reduction of bit rate and how complex the computation is. If you want to do it faster, lower latency faster, or you don't have the computes to do it, you can still have good looking pictures, but you're not going to get 100 to 1 compression. You might only get 20 to 1. You know what I'm saying? The bit rate will be higher. Does that make sense? Okay. So for HEVC, there's multiple commercial vendors now, including MediaKind. And you can get open source. There's 2 open source ones available here. With AV1, there are a few vendors that are just starting to come out with it. I'll list the names here. Open source, of course, is from AOL Media. And then you have a few other ones here. So where are they going to be? Or, well, let me know this. We have found a lot of improvement in a few months in the time. Like it used to take 32 minutes, like 6 months ago per frame. Now it's only about 1.5 minutes per frame. But we think they've gotten most of that out now. So we don't know how much lower it's going to get. But when they did that, they had to disable some tools. So again, you're trading off complexity so you get it faster, and the bit rate's going to go up. This is encoding time. So commercial AVC encoders now are real time, right? They're 0. And we're using that as a baseline. So it's not that it's 0%. We're just saying if you call AVC commercial your baseline point, and you're doing HEVC commercial, you're almost half the bit rate. See 40% bit rate reduction, but you're still in real time. There's a couple of software models here that are being done out there for AV1 that are just as good, but they're only gaining about 30 to 35%. So in this particular case, they're not as good as HEVC, but it's in real time. But again, it's no royalty, so you decide which do you want. Do you want no royalty? Do you want real time? Do you want? If it's not real time, then you can see the performance. It'll still be a little bit better, but it's not real time by about a factor of 10. But if you really want to get the best performance of it, it's way longer. It's going to improve. I'm not naysayer on AV1. My biggest concern with AV1 is not knowing whether it's truly royalty free or not. Hopefully it is. But so in all likelihood for traditional broadcast TV, for linear, absolutely not. You're not going to see AV1 using that in the near future. Maybe in a few more years as things mature, it's possible. It's really for streaming services, which you'd expect because those are the people that want to use it for streaming services. For traditional broadcast, you have to wait until the chips come out anyway. And again, it's an unknown performance. What are you trading off to get real time? If you trade off enough to get it to be real time, the performance is lower than HEVC, then you have to make a call. Do you want the best performance and then maybe you have to pay a little bit of a royalty for it? Or are you okay with it not being as good, but it's royalty free? Okay? So let's just throw a spanner in the whole mix here, right? Let's just make it even worse, right? The fact of the matter is, HEVC has been out since 2013. And it's usually every 10 years when you have a codec. There's a new one coming out from the same people that brought you HEVC, AVC, and MPEG-2, which is the joint development group of what's known as MPEG. You guys know MPEG, right? It's the Moving Picture Experts Group. That's ISO-IEC, International Standards Organization, International Electrotechnical Commission. It's a joint group of worldwide industry experts. But there's also the ITU, International Telecommunications Union, and you might not have heard this name before. Instead of MPEG, it's called VKEG, Video Coding Experts Group. But they really, MPEG and VKEG together are what produced MPEG-2 video, MPEG-4 AVC, also known as H.2. Well, I can say that. So there's two names for every one of these standards because of that. So because both VKEG and MPEG worked on it, MPEG-2 video is also known as H.262. MPEG-4 AVC video is known as H.264. HEVC is also known as H.265, right? So there's a new one coming out called VVC, Versatile Video Coding. It's the next gen. It's not quite 10 years out. It's only 7 years that they expect the standard to come out in October of 2020. Last October is when they did the final selection of test model. So there's a 2-year period where people are developing the coder and running it against a test model. And then the standard will come out of that. So the question is, how far along will AV1 get before VVC comes out? Because once VVC comes out, it's going to blow away AV1, performance-wise. But here we go. Yes, but we still have problems with the licensing of HEVC. Aren't we going to have the same problem with VVC? We could, except people are complaining about HEVC so much now, because I'll be blunt to you about this. This is my personal opinion. If it weren't for the licensing issues of HEVC being unresolved, there wouldn't be an AV1. Just wouldn't be. I mean, it would be for Google to use, but it wouldn't have any chance. This is no difference than Windows Media 9 versus AVC, which became simply standard VC1. Okay? It was around until AVC solved its licensing issues, and all of a sudden it disappeared, right? There's a forum called the Media Coding Industry Forum. I gave you the link here, the webpage for it. They're discussing IPR licensing up front. It's separate from the development group, which can't talk about commercial issues at all, because that's an antitrust thing. This is a group of people that's only talking about this stuff, and you are allowed to have a trade association, because it's not antitrust if it's done through a trade association. It's to make sure people agree on terms. You're not talking pricing, you're talking terms. Will you agree that if you have an essential patent in VVC that you're going to offer in this one pool? Those are the types of questions you're asking, and they want to work it out. And they want that to be resolved so that when VVC comes out in 2 years, there won't be any licensing problems. You're still going to have to pay a royalty or something, but at least it'll be a known amount. So you can see the advantage of that. So what's happening is it looks like the gains of it are going to be, it's about a 40% gain, somewhere between 30 and 44% gain right now in early results in real time over HEVC. This is significant boost. It's much better than HEVC and much better than AB1. The question is, will it make the market think of that? Okay. Updates on adaptive bitrate streaming. Okay, real quick on this one too. So we know that over the top is at the mainstream now, right? Live TV channels are available over the top. It's not like 10, 15 years ago when you were watching over the top, you know, it was a little picture this big, no resolution, right? At least with adaptive bit, you know, everybody here know what adaptive bitrate streaming is. I should start there, right? So the advantage of adaptive bitrate streaming versus previous methods is they used to pour down things onto the web. If you'd start playing it in your device, if there was no bandwidth on the web, because it's the internet, right? What happened? The hourglass came in and your video froze. That's not exactly a good video viewing experience. So the way that adaptive bitrate streaming is the client would request, your PC or your device, your phone, tablet, would request bitrate and would fill a local buffer. So latency was introduced in it to fill a local buffer. And then there's a high and low water mark in the local buffer. But if you did it right, no matter how bad the internet got, except if it was completely disconnected, because you can't plan for that, right? You would keep refilling that buffer while you're playing it out. And if you did it right, maybe you'd start like a minute late, but you completely fill your buffer up and down. So if the internet was slower, you'd request lower bitrate packets. And at the back points, which were called segments, or chunks, right? At the segment point, you'd switch from one resolution to another or one frame rate to another. Was it great? No, you'd see the difference, but it was smooth. It wasn't the jerky thing when the video froze. Your video would keep playing and hopefully the audio was running. So it was a great compromise in viewing stuff on the web. And actually looks quite good. Adaptive bitrate streaming looks good. Okay, pretty much everything today that's adaptive bitrate. So you have Apple's version, which is HTTP live streaming, which is HLS. Microsoft is called Microsoft Smooth Streaming. You know, there was another one from Adobe that's not too popular right now. They all are all HTTP based. Well, everybody knows what hypertext transport protocol is, right? Okay, so Dash was invented from MPEG, dynamic adaptive streaming over HTTP, to be like who here likes Lord of the Rings? Everybody likes Lord of the Rings, right? The one ring to rule them all, right? That's what Dash was supposed to do. It's supposed to say, we have all these different ways of doing ABR streaming. Can we have one, please? In other words, we don't want everybody having a trophy, like I said earlier. We want to have one method so we can do it better. Because there's already 5,000 different devices out there that do this differently, and you only want to encode once, right? So Dash tried to do it. They actually got everybody together except for Apple. It didn't quite work. There was a way to do it. They played games with it. Didn't happen. But we'll come back to that in a second. But that's what it's supposed to do. So this is basically, if you were streaming, you'd use one of these HTTP or dynamic or Dash versions would be one set. And then if you're, I don't know how many people here are from a cable, direct broadcast, satellite, digital, terrestrial television, or an IPTV service operator. But all these types of systems, you'd have your traditional television stuff, high quality, real time, but you're also playing on the internet. You want to have an over-the-top service, but they were done as two separate systems. Now they've gotten so good with these new adaptive streaming techniques, why do I have two separate teams of people working on this? It costs me a lot of money to do that, and it's not a toy anymore. I'm actually making money on my over-the-top service now, right? I could pay someone else to do it, like Netflix or Hulu or that, or I can do it myself with my content provider, or if I'm a managed network provider, I can run it over my managed network and give the user a better experience. So why don't I do this together? Why do I have to have two different services? So that's the holy grail, right? You want a unified head-end as your next generation ABR. What you do is you take your best coded version of your ABR, and that's your traditional broadcast one, because it's that good. It looks indistinguishable from what you were broadcasting. It's just formatted as ABR, so you just put a different packaging format on it. That's the next generation. You do this to reduce your investment, simplified operation, replace the separate silos. By doing this, and the way ABR works, because ABR's big advantage is what? You have these known segments, known time slots. Sure, the quality changes between them, but you know what it is. But that also means you can do what else? You can do easy program substitutions or ad insertion there. So you can actually do targeted, personalized television by using heuristics and analytics. You can do ad insertion that way. The same way, whether it's your broadcast platform or your top. And because it's targeted, you would just substitute a different program. How do you do that? There's a manifest file, right, that your device reads. And what that manifest is telling you, it's like reading a recipe. And I want 3 eggs, a cup of sugar, and you're going down the manifest file, saying grab this segment, grab that segment, grab this one. It's instructions for which segments to grab that's in your storage. And you're downloading these segments behind the scenes, filling up that buffer, but it's telling you which segment to get. Well, depending on your ad, it will tell you you change that one line in the manifest, grab this segment for the ad. Or you're not authorized to see the live match in your area, so we're going to give you a different program. You can substitute it. So this can all be done now. And the other thing is, if you're a traditional service provider, but you want to have an off-net, over the top experience, you can now offer your own service with a purely over-the-top set-top box, or, oh my God, not use a set-top box at all. Just use a standard client. A lot less expensive for you. You get a unified stack. This is the way to go. Okay? But here's the problem. As I mentioned before, first generation ABR, very low picture quality, very high latencies. It's not unusual to be a minute or 2 minutes late. Now, if you're watching a movie that you're buying on Netflix or something, who cares? So it's 2 minutes late. You're watching it in real time unless you're hitting pause or fast forward or rewind. I'm not talking about that. I'm talking about live events. Okay? You're in an apartment building and you're watching your beautiful over-the-top stuff. Thing looks great. And you're watching the World Cup and your team is playing and you're all excited. And the guys in the apartment next door paid 10 times more than you have for their really expensive TV system. And they're going, yeah, next door. And you're like, what? And then 30 seconds later, a minute later, they score the goal. That kind of ruins your viewing experience, right? So you don't want those long latencies. You need to get rid of long latencies. So the picture quality, we have something new that, again, if I was talking about my own equipment, I'd spend the whole section here talking about how we do constant video quality processing now. We actually change the bit rate, but keep the quality constant, loses less network bandwidth, so it helps out on ABR, and it uses less storage. So we've solved that problem. But the end-to-end latency, that's a hard one to overcome because the way that ABR works is you're trying to hide the network problem from you by using a buffer. So you're automatically, depending on your segment size, never going to be less than 30 seconds, because if your segment is 10 seconds long, you got to buffer 2 or 3 segments, because what if the network is messed up? You don't want to ever freeze. That's the freezing bad. Lower picture quality temporarily, as long as the audio is coming through, is good, right? Because you're taking advantage of that. So when we talk about these 3 new technologies, CMAF, the new holy grail, the one ring that binds them all, right? Common media application format. It has a new low latency mode. Works along with, that's how you actually code it and build the individual structures and have the commands for how to do it. HTTP 1.1 uses something called a chunk transfer encoding. It's how you can transmit the stuff over a network. So here's the way you code it better so that you can take advantage of it. This is the actual protocol that's doing the transfer. And then because Dash is your client, you have to update the client in order to understand the chunk transfer. So you need those 3 together. So again, the whole point behind this, let's look at the big picture here, is you want to encode it once. You don't want to encode it, no, let's say encode it once, you're still doing multiple profiles, right? Because that's the whole point. You want to have, if you're doing 4K, and you have 5 megabits or 10 megabits per second, and then the next one would be HD or something at 3, because you still have network issues. But that's not what I'm referring to. You don't want to encode it once for HLS devices, once for Samsung phones, and the other one's for LG, Sony. You want one format to encode, and it's called an adaptive transport stream. Here's the new thing that you get with CMAP. Now I want to package it and encrypt it once. Common encryption. and common packaging. Before, we couldn't do that with Dash because HLS was different. Now they've agreed on a common way of doing it, so now you got one packaging. There's a compatibility in how it's done between the different manifest files. So the manifest file, which is an MPD in the case of Dash or ISO-based media file format, is sent along with the two MPEG Dash devices, right? Apple compatible playlists are done or sent HLS, but the stream itself is identically coded under CMAP. It really is the one ring that binds them all, okay? But all these things have to work together. That's the end reason. So how it works is, with CMAP, you have your segment. Okay, so existing the way it works now, how many people here know what IP and B frames are for coding? Enough of you that makes sense? I'm not trying to embarrass you, I just want to make sure because I'm behind schedule, I only cover certain. Does anybody not know what an IP and B frame is? I can talk about it. Okay, good. So, as you know, in order for you to be able to substitute and reinsert something new, you have to start from an instantaneous decoder refresh or iframe. Yeah, one or the other. You have to do that, otherwise you can't substitute the segments. The way it works traditionally now is on the encoder side, you do full frame, intercoded, that's called the segment. That segment might be 10 seconds long in the case of HLS, that's not unusual. In the case of ISO-based media file form, it might be 2 seconds long, but it's still a long time, right? You code that, you can't send that segment out, or that fragment out, you can't, until it's all done. You gotta wait for it. So even if you do it in real time, you still have to wait. So the real time delay, if it's a live event, you're still running them live, but you're still 30 seconds behind, right? Then at the receiver side, oh, sorry, wrong drum, still stay here. At the receiver side, once you can request that segment, you have to wait until you get the old segment, the whole segment, sorry, not the old one, the whole segment, to decode it. Does that make sense? You can't send the segment until it's done, and you can't order it to come to the client until it's done, and then you can't decode it until it's done. So you can see all these delays that are in there. In the new one now, they changed the coding where they now have fragments, they're called MOV files, right? And the fragments, or media data itself is MDAT, right? You now can fragment it a little bit along the way. You still can't fully decode that because it's not decodable by a receiver, but at least you can transmit it early and you can receive it in the buffer and get it ready in your receiver. See what you're doing? You're faking the network out. You're sending it early and you're receiving it early. You still can't decode it so you get the entire fragment, but you're not waiting on transmitting it and you're not waiting on receiving it. So you've just taken, say, 20, 30 seconds out of it, just like that. Does that make sense? The idea is you want this to look the same, whether it's coming over the top or by traditional TV, because even traditional TV, you have about 2 or 3 second delay, so everybody has that. But 2 to 3 seconds versus 2 to 3 minutes, right? Okay. So HTTP chunking does the same thing. Now you have your camera and you can package or push this thing for a live event. It used to be one thing at a time. Now in your server can't reply with the content because it didn't know the full length of the segment yet. It had to wait. Now it can send the segments as they're being made. So it doesn't wait till it's done. It knows how long it's going to make the segment because it's been defined now. It's never defined before. So the other is done. And lastly, as I mentioned before, the Dash manifests have been changed now, as well as the playlist for Apple, right? Where now it's the start time of each fragment to start sending it, and it knows where the start time of the segment is even before it gets it. This will take all these delays out. It has a new parameter it uses. So based on all this, the client can start downloading that segment or the fragment of the segment as soon as it says it's the available start time, even though the whole thing isn't ready yet, because it's just start getting it. So you've basically eliminated all the delay except for the natural delay that you get over any network, which is the 2 or 3 seconds you're going to get anyway. So at the end of the day, and here I stuck my own company's equipment name in here, but you encode it live, right? If it's a traditional IPTV, a broadcasting thing, it's still an MPEG-2 transport stream. Ignore the TCP part here, just forget that. It's MPEG-2 transport stream right to the IPTV set-top box. It used to be then, you'd wait 30 seconds to a minute, and then you go through a packager, a different packager for Apple versus Android devices and Windows devices, and each manufacturer. Now it's one common CMAP packager, and you can use the same common encryption on that. If the output of that is then known as a CMAP LLC, low latency coded file using the new HTTP 1.1 transfer protocol, a low latency player, so there was a little bit of adjustment, but it's all standard using this, it's all software. And hopefully the point behind this is when that over-the-top player is playing it, it's at the same delay as the IPTV system traditionally would have it. And you can substitute cable or satellite for that, because it's similar delays, but there are different devices that do it, right? I hope that all made sense. Now, I'm about a half an hour behind schedule, so I'm gonna wanna start sharply at 12:15. Please stretch your legs, okay? So that you can get going on this. All right? But, oh, don't turn the lights on. For those that wanna take a quick break, go ahead. I'll stand here for a minute if anybody has questions. I just wanna make sure we start at 12:15. I need to take a bio break myself. I'm surprised I have any voice left, but, okay.
Quiero comentar que los que quieran ver un poco de una demo de HDR, tenemos preparado aquí.
Yeah, you'll see the demo.
¿Cómo te va? Todo bien. Anda bien. Entonces,